Hello, everyone. Welcome once again to this platform. We are very happy to have you. Kindly subscribe to our channel, like, share, and leave your comments and suggestions at the comment section. We warmly welcome you to our series on engineering mechanics. Today we are looking at analysis of trusses using method of sectioning. Let's see how to go about it, our problem and how to go about it. Find the force in member LK, BK, and BC in this diagram. When do you know to use the method of joint and the method of sectioning? You use the method of joint when you want to analyze the whole system in totality. However, if you are interested in finding the forces in some specific members, in this case, we want to find the force in LK, BK, and BC, then the appropriate method to use is to use the method of sectioning. Quickly, let's see how to solve the problem. Good. Anytime you are given a question on trusses, the first thing you need to do is to draw your free body diagram. And when you are done drawing the free body diagram, the first step in drawing the free body diagram is to detach the body from all kinds of supports. And once you have been able to draw the free body diagram, you use the equilibrium equations to analyze, to get the external forces. After getting the external forces, with the method of sectioning, you just cut through the members you want to determine their forces. So let's begin by drawing our free body diagram. The joint at A is a pin support, and the joint at B is a rocker. You can see that here you have some small circular things down there, which means that it is a rocker. If you were solving in an exam or in a question, you need to draw the free body diagram of the whole system again. But because I want to save time, I'm not going to draw the free body diagram. I'm just going to indicate my reactions at the support. A is a pin support, therefore we are going to get a reaction up here in the X. We can call this AX. And then we are also going to get another reaction in the, we can call it AY here. And then we are also going to get another reaction in the X, and that will be called AX. Then at G, we are going to, because this rocker will allow us to move horizontally, our reaction is going to be in the Y. It's going to be in the Y, and we can call this as GY. Good. Once you have been able to do this, the next thing for us to do is to determine the reactions at the supports using our equilibrium equations. And the equilibrium equations are sum of moment is equal to 0, sum of forces in the X is equal to 0, sum of forces in the Y is equal to 0. These are the equations we are going to use to determine the external forces. However, to use the first equation, which is sum of moment is equal to 0, we need to take moment at a particular point, and always remember that you take the moment at the point which has many unknowns or which has most of the unknowns, so that your work will be easier for you. Therefore, in this question A, we are having 2 unknowns. Therefore, taking moment at A will be very appropriate. Taking moment at A will be a convenient thing to do. Let's try to take our moment at A. Try to take our moment at A. So all the forces at A will go to 0, and our anti-clockwise direction will be positive. Therefore, we pick this force here and we multiply it by the distance to where we are taking the moment. Because the force is a vertical force, it's a vertical force, the perpendicular distance is going to be a horizontal distance. A horizontal distance. Therefore, our force is going to be, the distance is 2 times 7. Then we determine whether it to be clockwise or anti-clockwise. The system is like this. This is where we are taking a moment and the force is acting here. From the principle of transmissibility, we can bring the force up here. And you can see that when we bring the force up here, it's going to rotate this body in this direction, which is clockwise, and therefore it's going to be negative. And then we can also pick the next force, which is at point C, 5. The distance where we are taking the moment is also a vertical force. Therefore, the distance will be a horizontal distance. And the distance is 2 plus 2, which will be 4. Therefore, we have 4 times 5. And you check whether it will be clockwise or anti-clockwise. It will be the same as the first one you have just done. So that will also be negative, which is clockwise. Then we pick the next force. The next force here is 8. And the distance from, it's also a vertical force, therefore perpendicular distance is going to be horizontal. And the distance from this point to where we are taking our moment will be 2 plus 2 plus 2, which is 6, plus 2, 8 plus 2, which is 10. We have 10 times 8. That will also be clockwise. It will also be clockwise, it will be negative. And then we pick the last force, which is up there. Up there we have 2. We have 2 kilonewtons. We have 2 kilonewtons. And therefore, let's see how we are going to do our analysis. Let's see how we are going to do our analysis. Times 8, 10 times 8. And then we have the force up here, which is 2, because it's sorry for the breakage. Then we have 2, which is a vertical force. Therefore, the perpendicular distance will be a horizontal distance from this point to that point, which will give us 6. So we are going to get minus, that will also cause a clockwise rotation, minus 2.6. And then we have the G, which is going up, Gy times the distance from G to where we are taking the moment is 12. But now you realize that our Gy is up like that, and this is where we are taking our moment, is going to cause anti-clockwise rotation. That is why it's positive. Everything there is equal to 0. And from there, we can see that our Gy will be equal to 80 plus 12 plus 20 plus 14. And 12 Gy. Therefore, Gy will be equal to 126 over 12, and our answer will be equal to 10.5 kilonewtons. From there, we can get f of s is equal to 0. We only have one x, which is ax. Therefore, we can say that our ax is equal to 0. And then we can write for y, sum of all fy is equal to 0. And from there, we can see that ay, which is moving upward, and so it will be positive, minus 7 coming down, minus 5 is also coming down, so it's negative, minus 2, which is also coming down, minus 8 coming down, plus Gy, which is moving up. But we have calculated, or it will be equal to 0. We have calculated our Gy to be 10.5. So AY plus 10.5, and all this, when you sum them, you are going to get minus 22 is equal to 0. Therefore, our AY will be equal to negative 11.5 kilonewtons. Once you are done determining the external forces, what you need to do is to now section the part which we want to determine the forces. We need to, in this case, we are asked to determine the force in LK, BK, and then BC. Therefore, we are going to section like this. We are going to cut through those members. We are going to cut through those members. We are going to cut through those members. And once you are done cutting through the members, you realize that now we are going to get two parts. We are going to get two parts. We have this side here, and then we are also going to get this side. But realize that when we analyze the one on the left, it will make our work easier. Therefore, let's just draw a free body diagram for that side. Our free body diagram is going to look like this. This side is A. AX was 0, so we can just indicate for AY. We're getting negative, therefore it means that it is coming down. AY, which is negative 11.5. And then let's take that this point is L, and this point here is B. And we have cut through L to K. Let's assume that this point was our K. And then this point was our C. This point is our C. But we have cut through those sides. Therefore, the member BC is going to have a force like this. BC, we can call it force BC. FBC. And the member from B to K is going to have a force like that, which you can also refer to it as force BK. Force BK. Then the member from L to K, which you have cut through, is also going to have a force. You can call it force LK. Good. And we know that the distance from C to K, the distance is given as 3 meters. 3 meters. Now you realize that from A to C is two divisions. This is the first division. The first division is here, and this is the second division. So if the second division is 3, then we can calculate the first division. From ratio and proportion, we can say that if the second division is equivalent to 3 meters, then the first division here will be equal to x. And from there, we can say that the length is equal to, let's take it to be LB. The length of LB is what we are looking at from this point to that point. From there, we can say that length LB will be equal to 1/2 times 3. And from there, our length of LB will be equal to 1.5 meters. Once you have been able to determine that, so this side, the length of this side is going to be 1.5. This is A. Good. And we know that the horizontal distance from B to C is 2. This side is 2 meters. Therefore, if we draw also a horizontal from here, the length is going to be 2 meters. It's going to be 2 meters. Therefore, if this is 1.5 and from this point to that point is 3, then it means that from this point here up to K here will also be equal to 1.5. Will be equal to 1.5. I'm talking about from this point to that point. But from this side to K will still remain as 3. Now what we are going to do, we want to resolve you can see that the force FLK is not in the X or in the Y, and then FBK is also not in the X or in the Y. Therefore, we can draw a diagram for them and resolve. For FLK, this is FLK, and this is L. The horizontal distance is 2, and then the vertical distance from this point, from where L is, from where L is to where K is 1.5. So from here, we can calculate the hypotenuse. The hypotenuse will be equal to the hypotenuse from L to K. The hypotenuse from L to K is going to be square root of 2 square plus 1.5 square. And that is going to give us, I think that should be able to give us a value of 2.5 meters. Therefore, the length here is 2.5. And the force is moving this direction here. We are just considering the force from this point to that point here. This point to that point. Now, from that point, you will see that we move this distance on the X. Don't forget that our direction still remain like this. To the right is positive, on the X, to the left is negative. Up is positive, down is negative. Therefore, you can see that we'll be moving to the right, which will give us positive for X. Then we are going to get FLK positive times the horizontal distance, which is 2, over our hypotenuse, which is 2.5, which is 2.5. We can do the same for Y. You can see that from this point, you also be moving up on the Y. Moving up on the Y. Y will also be positive, but the distance is 1.5. Therefore, we have FLK times 1.5 over the hypotenuse, which is in this case is 2.5. And from there, we would have resolved force FLK into components. We can also resolve force FBK into components. The horizontal distance here is 2, from B to C is 2, and up from this, we realize that force FBK is moving all the way from B to K. It's moving all the way from B to K. Therefore, the vertical distance is 3. Vertical distance will be 3. And now the hypotenuse, we need to calculate the hypotenuse for BK. From B to K will be equal to square root of 2 square plus 3 square. And that should be able to give us a value of 3.6. Therefore, the hypotenuse here is 3.6. And from there, we can resolve our force. You can see that we'll be moving right on the X, which will be positive, and up on the Y, which will also be positive. The X distance is 2, and the hypotenuse is 3, and our force is FBK. So this will be our S component, and our Y component is going to be 3. This is our S component for FBK, and our Y component is going to be 3 FBK times 3 over 3.6. 3 over 3.6. And for that, we have been able to resolve FBK into S components and also to Y components and And from there, time is set for us to be able to calculate for our unknowns, the force in those members. Allow me to clean this side so that we can be able to get space to calculate our forces in those members. And don't forget that we are still going to use the equilibrium equations, which is sum of moment about a point is equal to 0, and then sum of forces about X is equal to 0, and also sum of forces about Y is equal to 0. Now that we have been able to resolve all forces which are slanted into their component form, we can be able to calculate that with ease. We can be able to do that with ease. Good. So now let's use our equilibrium equations. For our equilibrium equations, now we can, looking at the free body diagram, you can see that we said, looking at the free body diagram, you always take moments at the point which has many of the forces, many of the unknown forces. Here you can see that at B, we have two unknown forces. We have FBK and FBC at B. Therefore, we can take our moment at B. We can take our moment at B. Don't forget that at B, our diagram will look like this. This is B. We have FBC going this way. We have our A at this point. We have resolved FLK into components. So we have the vertical. Sorry for that. Let me clean this and bring it a bit down so that we can all see. Don't forget that that side, this is L, and then the force at L, the distance here is 1.5. We have a force at A, which is 11.5, pointing downwards. It's pointing downwards rather. Sorry for that. It is pointing downwards. And then force FLK has been resolved into components. We have the Y component here, and then we have the S component here. And those values are what are here. The S component is FLK times 2 over 2.5, and the Y component is FLK times 1.5 over 2.5. So from here, if we are taking moment at B, this is FBK. Taking moment at B, this force will go to 0, this force will go to 0. Therefore, we can say that taking moment at sum of moment at B is equal to 0. Anti-clockwise is positive. From there, we are going to get our result as 11.5. 11.5. Let me write the S component of the force, the various forces. So for FLK, the S component is equal to, the S component for is going to be 2 over 2.5 times FLK. And then the Y component is equal to 1.5 over 2.5 times FLK. And then the one for FBK, for force FBK, the S component is equivalent to 2 over 3.6 times FBK. And then the Y component is now 3 over 3.6 times FBK. Times FBK. And from here, we are going to get our moment about B as equal to 11.5. 11.5 times the distance where we are taking the moment. You know that the distance from A to B is 2. So times 2. But will that give us a clockwise or anti-clockwise rotation? We can see that if the force is applied like this, and this is our distance, this is where we are taking our moment, that from the principle of transmissibility, the force can be brought here, which means that it is going to rotate the object in the anti-clockwise direction, and that is going to be positive. And that is going to be negative. Okay. Let's maintain our definition that our forces are going in the anti-clockwise, but whatever, 11.5 times 2 minus this F, the S component of FLK. The S component, this is the S component. The perpendicular distance is 1.5. So we are going to get 1.5 times FLK times 2 over 2.5. That is also going to cause a clockwise movement. Looking at where the force has been applied, is going to cause a clockwise movement. So it is going to be minus, and from there we can, this is equal to 0. So from there we can say that our FLK will be equal to 11.5 times 2 all over 11.5 over 2 all over our force all over the value of that will give us 1.5. 1.5. Sorry for this. $11.5 times 2 over 1.5 times 2 over 2.5. And from here, FLK will be equal to 19.2 kilonewtons. Once you are done determining FLK, we can also use our second equation, sum of forces in the y is equal to 0. And as usual, if we move up, it's positive. Therefore, we are going to get the y components for FLK will be 1.5 over 2.5 times FLK minus our y for this one was negative, so we brought it down. We brought it down, which will give us minus 11.5. Then minus 11.5, and at B, we have a force of 7 kilonewtons, which is pointing downwards. 7 kilonewtons, so minus 7 pointing downwards, plus the y component of FBK, which is now 3 over 3.6 times FBK is equal to 0. Then from here, we can substitute the value of FLK into the equation. And we can see that from there, allow me to erase this area so that we can get enough space for our solution. Yes, so from there, we can write that. From there, we can write that FBK. We can write that FBK will be equal to, when we substitute the values in, we are going to get 6.98 over 3 over 3.6. And from there, our FBK will be equal to 8.4 kilonewtons. But don't forget that you have already calculated FLK and the value is 19.2. So just substitute this into this equation and FBK will be equal to this. And from here we can write sum of f of x is equal to 0. For f of x is equal to 0, we have FBC, the S component, this force which was down here, FBC plus the S component for the other two forces, which we have 2 over 2.5 times FLK plus 2 over 3.6 times FBK is equal to 0. And from here we can see that FBC plus is equal to, will be equal to negative 2 over 2.5 times 19.2 minus 2 over 3.6 times 8.4. And from there, FBC will be equal to negative 15.36 minus 4.67. And FBC will be equal to 20 kilonewtons. So with this, we are done solving the problem. That was very simple. I don't know, but if you have any comment, any question, or any suggestion, you can let us know, and we'll be very grateful to assist you in that regard. Thank you very much for staying in touch with us, and we wish to see you in our next video. Once again, thanks for watching. Kindly subscribe and hit the notification bell. Bye-bye for now.